that unclear?
What?
No, I get that.
Okay, let's start.
That's the formula. Yeah.
So we're going to pick up again with linear approximation. Going to do one more example of that to make sure we know what's going on there, and then we're going to move on to the marginal functions. All the handouts I gave you, they're online on the website in case there are not enough copies to go around. Remind me of the linear approximation formula. Okay, so we're reviewing linear approximation. So it says that f of x
Equals f of a. It's close to.
is approximately close to f of a plus f prime of a times x minus a. One thing you can notice is that this part here is actually the tangent line. Y equals f of a plus f prime of a times x minus a is actually the equation of the tangent line. At x equals a. So that's something you can notice. So we're using the tangent line to approximate the value of a function. When is this approximation good? What are the things that we need here for this to work or be a viable option? When can we consider this true? When is f of x almost this expression? Yeah?
When x closest to a, or f of a.
X is close to a. Right, so our points have to be close together. This is a method that it has to work very locally. And the closer these 2 points are together, the better the approximation will be. Okay? And of course there are other things like f has to be differentiable, all that stuff. But yeah, if f prime exists and your x is close to a, this approximation is useful because the tangent line and the function do the same, do pretty much the same thing once you zoom in far enough. And we actually did an example of this where by hand we worked out, I believe it was the square root of 3.99, and we got that correct to a lot of decimal places. I believe 4 was rounding. Let's do another example. Let's do the cube root of 8 points here. Let's do that. Right, so as you saw in the review, and I did post a review, and it freaked a lot of people up. Everyone was like, do we have a test tomorrow? No, the test is after the break. You know. I mean, what kind of guy would I be if I posted the review like the night before the test? The test was due. Come on. It's like, yep, you guys got 12 hours. Time to have all the time in the world. Okay. Did you have a test tomorrow? No, this test no. But the test is right after you come back from the break. So let's actually do this one. So run me through the steps again. And as you can see, there was a problem like this on the test. So it's again, it's the same sequence of steps. We're not going to get too crazy here. So the question is pretty much always going to look something like that. Use linear approximation to estimate this thing. And what's the first thing we need to do? Yeah?
F of x and x we define.
Right, we need to define our function. What function are we going to use in order to make this approximation? Okay, so in this case, what do you think? Yeah?
You don't have to say it.
Cube root?
Yeah.
Cube root of x seems to be a nice function to use because we want to approximate the cube root of something. So let's say we do the cube root of x. Second thing we want to do, but we'll use it eventually, so we'll immediately just find the derivative. Hopefully we chose a differentiable function to approximate the thing that we care about. So in this case, what is going to be f prime of x?
1 over 2x to the 20.
Right, So you would think of this as x to the 1/3, and you find the derivative using the power rule, so that's 1/3 x to the minus 2/3. You can also think of this as 1/3 x to the 2/3. You can also think of that as the cube root of x and squared it. And your 3x is positive, so that's the derivative. What do we need to do next?
Find x.
Well, finding x isn't going to be tough. It's going to be the guy you want to approximate. So here I would set x equals 8.01. So x is the input value that you want to approximate your function at, and a is something close to x for which we know all the information already. Okay, so what would I choose a to be here? 8. Right? That's the closest thing to 8.01 that I know the approximation of, that I know the cube root of, and they're pretty close. They're off by 1/100. Okay, so that's your x and your 8, and then 4 just plug into the formula. Right, so you're going to use the fact that f of x is approximately equal to f of 8 plus f prime of 8 times x minus 8. So really when we look at the cube root of 8.01, what we're looking at is f of 8.01. That's our x. This is going to be approximately equal to f of 8 plus f prime of 8, 8.01 minus 8. Just plug in the numbers. So my x I put here, my a's I plug into the function, x is this, a is that. And now we just find the numbers. What's f of 8? 2. It's just 2. Plus, what's f prime of 8? Plug in 8 here.
1/12.
Right, so if I plug in 8 here, take the cube root of 8, I get 2. Square that, I get 4. Multiply by 3, I get 12. And 8.01 minus 8 is just 0.01. Now let's simplify that a little bit. So this becomes 2 plus, well that's going to be 1/1200. This times 2 is 2400, so it's 2401/1200, or approximately. I think I actually wrote this down last night, so I'll just tell you what that is approximately. This will be 2.000833, and the 3's will be forever. And just for some comparison here, the actual answer is 2.00083296. So we were right up to, with rounding, 6 decimal places. Pretty nice. So that's how you use a tangent line to approximate a function of a point. Any questions on this? And again, problem is always going to be stated this in a similar way. These are usually always going to be the steps. The hardest part of the problem is first coming up with a function, but it's usually going to look like the thing you want to approximate. You're just going to replace the weird number with an x, right? And then you have to figure out these guys, but then the rest of it is just sort of plug and chug. And it kind of shows you the power of the derivative to approximate a function, or the tangent line. So this is one application of a derivative. And the topics where we will be covering in this section and beyond are really about applications of derivatives. So I'm not really going to teach you how to differentiate any new functions at this point. you've learned all the derivative rules you have to. Our focus now is going to be on applying them, which brings us to the next topic in this section, which is going to finish off 3.2, marginal functions. So there's a handout for this, and I gave you a handout for a couple other things. A lot of things we'll be doing from now on is going to be work. So if I can't bother writing all the problems down on the board, I'll just give you guys a handout with the problems on it. So you have the marginal functions handout, and there's a copy of it on the website in case you didn't get a copy, you can use your copy. So let's just talk basically about what this is. So let f(x) be a function, then, of course, if it exists, f prime of x is its marginal function. So it turns out marginal function is just another name for the derivative, essentially. And we'll talk about why we sort of give it that name soon. So for example, let's say you have c of x equals a cost function. So this is a function that gives you the cost of x items for some reason, by some data that you have. Then if you take the derivative of this function, you call that the marginal cost. So the derivative can be called the marginal function. This is usually, when we're talking about this, it's in an economics/business context. Right? In that context is where you'll see the word marginal used, because it kind of tells you what happens along your margin. In what sense? I'm going to tell you now. Again, we're going to use the approximation capabilities of a tangent line to come up with some sort of theory here. Why do we care? Let's do it. Consider a cost function. I'll illustrate with a cost function. By the definition of the derivative, what is c prime? It's going to be the limit as h approaches 0 of c of x plus h minus c of x all over h. And basically what that means is, this means if h is small, if it's getting close to 0, right, we'll put small in quotations, basically what you can say is, and this essentially comes from the linear approximation formula as well, is that c prime would be approximately equal to this guy. By essentially the same reasoning that we use the linear approximation formula. And so now we make an assumption. Suppose our x is taking on large values so that h equals 1 is considered small. And this is where it sort of comes into business. Usually now our x is going to be representing some kind of product that we're mass producing, usually, or mass selling. Okay, so x is going to be in the thousands or tens of thousands. You imagine that there's this large company producing a certain amount of products. They know about their cost function, and so now they're looking at the marginal cost function. X is so huge that h being small is 1, which is pretty much as small as it can get, right, without coming to 0. And so in that situation, you end up with c prime is approximately equal to, literally just plug in h equals 1 into this formula. And this is the essential equation in the marginal function interpretation. That the derivative actually approximates that quantity. What does the right side of this quantity represent? When you see this expression, c of x plus 1 minus c of x, what does that mean? How would you interpret that? Yeah?
The difference between producing one more unit and like the difference in cost between producing one more unit versus the original amount of units that we produced.
Okay, so this is difference in cost of producing or selling or whatever x plus 1 units and x units. Or in other words, we can think of this as the additional cost by producing one more unit. So it turns out the derivative can approximate this quantity, and what that quantity is precisely this interpretation. It's the additional cost of producing one more. And that's sort of an interpretation that's taken across the board when you're talking about marginal functions. So you don't have to just stick with cost. This was an illustration. You could apply this to any function. The usual functions in business are profit, revenue, and all that. So if you talk about marginal cost, this is the cost that you would have by producing one more unit. If you talk about marginal revenue, that's the additional revenue you would get by producing and selling one more unit. If you talk about profit, that's the additional profit you would get by producing one more unit, etc. Right? So it talks about, when you're looking at marginal functions, you're talking about at the edge of production. Okay, if I'm here at point X, what if I tiptoe a little more and pass that point? What does the picture look like now? Right? Just like you want to push the margins a little bit, and you want to see what kind of situation you end up in. What you can do is you can use the derivative to talk about that situation. And when you consider the derivative in that way, usually you're considering it as a marginal function, a function that describes what happens at your margin. And this can have very great predictive power. So you can kind of know, you can use the derivative to keep track of what you're doing, and you can always know ahead of time, should I be sort of pushing more? Should I be producing more? Should I be selling more? Or should I be pulling back? You can tell that by looking at the derivative. And the purpose of this is that the derivative itself is often a lot easier to work with than the original function. So let's do an example here. So on the marginal functions handout on page 2, we have 2 examples. The first one is just to sort of get you used to the idea, but we're going to see the benefits of it in example 2. This is example 1. On the handout. Suppose the cost of producing X glow in the box boxer shorts is this function. Now, cost functions are usually given. You can't really derive them. It depends on the situation. It depends on how many workers you have, what spaces you're in, if you have business loans, all that sort of stuff. Right? So a cost function has to be sort of given to you. There's nothing inherently mathematical about a cost function. It highly depends on the situation, and that would require data, statistics, probability, all that kind of stuff. That's where that would come. So somehow you obtain this cost function, right? So this tells you the cost of producing X boxer shorts. So you can say, how much would it cost me to produce one pair of boxer shorts? When you plug in X equals 1, that would cost us $5. Okay? How much would it cost us to produce 2? Right? Then you plug in 2 here. So that would give you 8 plus 6. So that would give you $14. Okay, so this is just a function that tells you, okay, plug in a certain X value, it tells you what's the cost of producing that many boxer shorts. So that's the situation we're in. Now A, what's the additional cost to raise the production level from 10 to 11? How do we do that? What is additional cost to go from 10 to 11? Yeah?
You just plug in 10 and 11 and just find it between the two.
Exactly. Right. This is the function that gives us the cost, so we can find the additional cost by just taking C of 11 minus C of 10. This is the cost to produce 10, this is the cost to produce 11. And find the difference between the two, I can get the additional cost of going from 10 to 11 in production. Now what is that equal to here? I would simply plug that in here. This is 2 times 11 squared plus 3 times 11 minus 2 times 10 squared plus 3 times 10. What's that equal to? Huh? The whole thing is 203 or?
45.
Huh?
45.
Does that go to 45? Is that 45?
Yeah.
Okay. So 45. So the additional cost of producing the 11th boxer shorts is $45. It's an expensive pair of boxers. Let's look at B though. Now in B we're asked, what is the marginal cost when X is 10? How do you find the marginal cost? Yeah?
You can do the function in this way in time.
Find the derivative, and then we're going to plug in 10. So what does the derivative look like here? 4x plus 3. So we want C prime of 10. That's going to be 4 times 10 plus 3. And that's 43. Now a couple things I want you to note here is that one, that's actually not far apart. They're pretty close together, and we're only talking about 10 items here, so that's not even a lot. Okay? Usually X will be in the thousands and we'll get a lot closer, but we're off by like 4%-ish, and it's not a bad approximation. So what this number is, how you'd interpret this, is that this is an approximation of that. This is the actual value, but I use the derivative to approximate that value, and they're not that far off. That's one thing I want you to realize. Another thing I want you to realize is that look at the computation that we had to compute to calculate the actual value versus the computation that we had to compute using the derivative. Right? This is kind of one of the benefits right there alone. Right? So if you have, and again, assume you're a large corporation and you're running computers to figure out how things are moving, you're doing thousands and millions of these calculations at a time. You know, compared to this in a computer that's doing this millions of times. You know, and really, no one sort of runs on these simple models anymore. The mathematics can get pretty complicated. So you do want to cut down on computation as much as possible. And this is just sort of, you can sort of see an illustration here, how computation using the derivative versus using the actual function can be a lot easier. Here we have to do two huge computations and then subtract them. Here we just do one small computation. And so we can almost cut our computing time in half, which compounds on itself. So that's the two things I want you to take away from this. This is an approximation for that. Not a bad approximation considering we're only doing 10 products here, which is not how it would be used in practice anyway. That's pretty good, I think, for 10. Let's move on to example 2. This one's a bit more involved, and it would more resemble a problem that you would see on a test or a quiz, I think. Maybe not as many parts. And as we go through this, I'm going to be defining some functions for you to be used at a later point. So in example 2, we're given a demand function. T is equal to 25 over radical x. What's a demand function? Did any of you take economics yet, or microeconomics or anything like that? You would have seen that, I think. What is the point of a demand function? So a demand function describes the price at which consumers are willing to consume X items. In other words, this is telling you if you want to sell X items, this formula gives you the price that you should sell them at because consumers will consume X items at that price. So if you want to sell only one item, you only want one person buying it, you should charge $25. If you want 100 people buying it, you should charge $2.50. This is sort of something that, again, it comes through a lot of market research. Another very common function that's sort of seen side by side with this guy is called the supply function. And this describes the price at which suppliers are willing to produce X items. Right? These are often not the same as a demand function. In fact, they're categorically different usually. Usually if I put price here and number of items here, a demand function will always be an decreasing function, right? As price increases, the number of things that people buy will decrease, right? People buy more Toyotas than Ferraris. This is sort of conceptualizing the demand function, right? So as the price increasing, says people would demand less of that product, so they will actually buy less of that product because it eventually gets too expensive and they don't have enough resources. The supply function, on the other hand, tends to always be increasing. Right? If you're going to pay more for a product, a supplier will tend to want to supply more so that they can increase their profits. So supply functions are usually increasing. And then there's this magical number right here, This is called market equilibrium. So that's sort of the sweet spot. That's where the suppliers can produce as much as they want to get as high a price for that object as they want, right? If they produce more than that, they'll have more supply than there is demand, and so they'll have inventory that they can't sell. If they produce less than that, then they're not producing enough, and people will always demand more, and customers won't be happy, right? So that's sort of the situation we're ending up in. So this I just gave you is the demand function. So basically what you can think of this as is the price at which you can reliably sell X items. Right, so you tell me an X, I can tell you what price you should charge in order to sell that many items. Okay, that's what your demand function is. So in other words, whenever you see a demand function in one of these problems, it's talking about the price that you can sell to the consumer. The first problem is to find the marginal revenue function. How do you find the marginal revenue? What is marginal revenue? What is the marginal of any function? Yeah? It's the derivative of the function. So if I ask you for marginal revenue, I'm asking for the derivative of the revenue. Okay? Which means we first need to find the revenue. So how do we find revenue? How do we find a revenue function? What's the most naive way to find revenue? How much money will you make by selling X items? Yeah?
The price of the item times the amount of items.
Price of the item times the amount of items. That's just X times P. This is a definition we can take now. R of X is going to be X times P. This is the number of items times the price per item. And of course I put it in a box because I expect you to memorize this at this point. That's how you find the revenue. So in this case, our revenue function will be X times P, and P was given. P is the price that we can sell to the consumer. So that's going to be X times 35. So this means that our revenue function is 25 radical X. That's not the point. And with that, we can find the marginal revenue. This is just our time of X. And what's the derivative of that function? Derivative of 25 radical X. Huh? We can use product rule. 25 is a constant.
Oh, you said.
So leave the constant alone and differentiate the function. Derivative of radical X is 1 over 2 radical X. And so this is 25 over 2 radical X. That's our revenue function. That's our marginal revenue. Let's just do part B and then we'll get out of here. We'll continue the rest on Wednesday. And we don't have class on Friday because spring break starts on Thursday. Right?
Yeah. I'm tired for spring break.
I'm not afraid to hide my enthusiasm. Professors are always like, kids are just like it up. Professors are happier than students to get spring break. You have no idea. I'm like, yes, I don't get to see these kids for another week. Okay. So it says here, what is the marginal revenue? When x equals 10, 100. Not that I don't love you guys, but you guys are a lot of work. Getting sick just trying to be here on time every day. Okay, so this just means you plug in 100 into the marginal revenue function. This gives you 25 over 2 times radical 100. That's 25 over 20. Which is what, 5 over 4, so that's 1.25. What's the interpretation of that number? How would you interpret that number, 1.25? When you see that number, you find the marginal revenue, you plug in 100, you get the answer 1.25. How do I interpret that number? What does it mean to me? What does a marginal function measure? Yeah?
For every additional quantity that you make, it's going to be $1.25 more.
It's the additional revenue. You don't really want to think about it in general for every additional quantity, because the situation might change when you produce that quantity. So you can really talk just about the next one. So it's the additional revenue earned by producing just the next one. The 101st item. Your situation might change after you produce that item, so you can't really predict. Right? You never know. There might come a point where once you push past that point, now you have to hire more people, you have to get a bigger space to rent. Situations can change the more you sell something. But what the marginal function does, it just tells you what happens at the margin, what's kind of going, if we just push a little more, what's going to happen. And we can expect this much more revenue. We'll continue that problem there. You guys can probably try that out on your own. We'll finish up.
Only starts 10 o'clock.
Maybe like,
There's also